Okay, we're going to talk about a really powerful graphing technique, and at the end of this class period, I don't expect 100% of you to understand 100% of what we're going through here, but this is kind of a grab your attention at the beginning of the school year and learn. Even though there's some things that we're pretty good at in math, like graphing functions such as this, there may be a more conceptual approach rather than just grinding it out mechanically. And I think some of you will amaze yourself what you know at the end of this class period. So go ahead and grab some graph paper if you have it, but you shouldn't need graph paper. You can just make little thumbnail sketches, something along the line of this. And just graph each of these four functions. Certainly shouldn't need calculators to do this. We're not looking at putting a whole bunch of points on here, but maybe 5 points or so, and get those connected and to come up with an idea what these look like. And then we're going to talk about combining these functions together. So as you're going ahead and doing that, feel free to pause this video, work ahead of me, or you can follow along with me here. I'm going to go ahead and sketch these, and I certainly don't expect that many of you would need to do a T-chart on here, but if we were, this would be what I call the freshman approach to graphing. Put 0 in for x, 2 times 0, 0. Put 1 in for x, 2 times 1, 2. I'm going to jump to 3 in, 2 times 3, 6. Of course, negative 2, 2 times negative 2, negative 4. It gives me a pretty good sampling of points. And of course, we all know what this line looks like. 0, 0, 1, 2. 3 gets me up to 2, 4, 6. Negative 2 gets me down to negative 4. And of course, you could have done a slope intercept thing to this to save yourself a little bit of time, but here's our function, although I missed the line. Okay, how about y equals 4 here? Well, that's pretty easy, and a lot of people will mess this one up because they think, well, y goes up and down, so the graph must go up and down at 4. But if we just T-chart this, the rule says y is going to be 4. There is no rule for x, so x can be whatever it wants. Like 0, 2, negative 3, anything at once. So I get points at 0, 4, and 2, 4, and negative 3, 4. And of course, I know this is elementary, but first day of school. There's our function y equals 4. Y equals x to the 5th. Well, 0 to the 5th is 0. 1 to the 5th is 1. Negative 1 to the 5th is negative 1. And 2 to the 5th is 32. And negative 2 to the 5th is negative 32. So by the time I get out here to 2, I will have well run off this graph. So this thing gets steep in a hurry. Might look something like that, and something like that. Okay? And here is I may even put something down here, just a little reference, like this would be somewhere on down, dot, dot, dot. This would be the point negative 2, negative 32. Okay, now y equals negative 5x cubed. xy, when x is 0, 0 to the 3rd is 0 times negative 5 is conveniently 0. And when y is 1, or when x is 1, excuse me, 1 to the 3rd, 1 times negative 5, negative 5. 1 gets me down to negative 5. And when y is negative 1, negative 1 to the 3rd, negative 1, times negative 5, positive 5, negative 1 gets me up to 5. Looks like a straight line. Of course, we know better. It's not a straight line. Let's go ahead and check 2. When I put 2 in here, 2 to the 3rd, 8, times negative 5, negative 40. So again, we're way, way, way down. By the time we get to 2, we're way down negative 40. Negative 2 would give us 40. So maybe we look something along the lines of this. We know there's a curve, a little wiggle through there. And dot, dot, dot. Up here we might have a point. You know, if we could go far enough, this would be the point negative 2, 40. So there's 5 functions, no big deal. Okay? But we're going to start talking about combining these functions a little bit. So I want to do some comparing and contrasting. And you hopefully have these graphs or some semblance of these graphs drawn at your seat or at your computer if you're playing along with the video. And you can refer back to those. I'm not going to come back to these. I'm going to assume we have some idea of what these things look like. And we're going to just compare these 4 functions as if they were in a race with one another. And I would say if this is, let's say, function A, this is function B, C, and D, my question to you would be, which of these functions is the most powerful? In other words, if they were all racing, and let's disregard the negative. If they were all racing right now, are they all starting at time 0, and we allowed these things to run, who would go the farthest distance? In other words, which graph is going to be the highest, which one's going to be the lowest when we put in values for x? Which one is ultimately going to be the highest, lowest, which is the strongest function? And I would suspect in a class of 30 or so students that some of you at this time, even as strong as students as you are, being in honors pre-calculus, would be pretty confused by that statement. And I would suspect some of you would say that this one is the strongest. And I understand your reasoning for that. And I would think that some are confused, but in a good confused way, because there's a question that really needs to be asked to answer this. And that is, how long are we racing for, or how far are we racing? In other words, what kind of values are we putting in for x? For instance, if I start at time, let's say x is time, at time 0, function A has gone 0, function B is already at 4, function C is at 0, and function D is at 0. And if I said which one of these is the most powerful function at x equals 0, you should say B is. It's moved along the furthest. It's moved up or down the furthest. And if we say, well, what's happening when x is 1? A 2 times 1, this would still be 4. C would be 1 to the 5th 1, but D would be 1 to the 3rd 3, 1 to the 3rd 1 times negative 5, negative 5. So by time we get to 1, D is our strongest. Well, let's continue the race for a little bit. Let's go to 2. 2 times 2, 4. This function's always 4. 2 to the 5th, 32. 2 to the 3rd, 8 times negative 5, negative 40. And D is still the strongest. Oh, so D is going to be the strongest. Well, function C made up a lot of the gap, 1 to 32. Let's take this out to 3. Function A, 2 times 3. Function B is always 4. Function C, 3 to the 5th, 243. Function D, 3 to the 3rd, 27, times 5, 135, but negative. And we see that, oh, it looks like ultimately, if we let the race go on long enough, perhaps C is our strongest function. But back at time 0, B was our strongest function. The only one who hasn't been our strongest function so far is function A. Does function A at any time become our strongest function? Well, I'm convinced if I continue on beyond 3, function A is not going to be my strongest function, but let's consider just point 1. 2 times point 1, point 2. B is always 4. C, point 1 to the 5th. Point 0, 0, 0, 0, 1. D, negative 5 times point 0.1 to the 3rd. Point 0, 0, 5, but negative. But what do I notice about A? A hasn't become stronger than B, although I know down the road A will become stronger than B. But what has A done? A has become quite a bit stronger than C and D. So what I want to talk about is what happens when we put all of these functions together. For instance, we think of the function f of x let's start with x to the 5th minus 5x cubed plus 2x plus 4. And let's think about this just for a moment. Where does b really exert the most impact on this function? Well, it is dominant on this function right here at 0. And where does function A start to kind of influence this graph? Well, most definitely around point 1, when we're at point 2 versus virtually 0 versus virtually 0. Point 2 is not much, but it's a lot compared to virtually 0. 2x is going to exert some some influence on this graph. Let's look at function D. Function D, it doesn't take long for function D to start saying, you know what, I'm in charge of the rest of you guys here. By the time we're just out to 1, function D has the strongest result. And function D continues to be the strongest influence on this graph for some time. But ultimately, function C is going to say, you know what, it's mine from here on in, kids. So this is a graphing technique that I refer to. Well, before I do that, I'll tell you where I got the name. I'm sure some of you have run track in junior high, and a number of you, I'm certain, have moved on into high school track. And you could probably tell me what a medley relay is. A medley relay is a relay where each runner may run a different distance. There's different medley relays. And it's kind of like gears of a sports car. You've got gears that are specialized, and I'm sure most, if not all of you know that first gear is really good at getting the car rolling, getting started. It's really quick off the line, but ultimately you probably want to be in a 5th gear or a 4th gear if you're traveling at highway speeds, but along the way you kind of pass the baton to the next gear. So I would say that our sprinter, our first leg of the relay, is here. This person at 0 is already 4 ahead of everybody else. And the next one who's going to start to exert itself at point 1, this would be our second runner, or our second gear. Third gear, and ultimately 4th gear, y equals x to the 5th, is ultimately going to take over. It only takes till less than 3 till it's the dominant function. Let's take a look at this one. I'm going to let you go ahead and graph this one on your graphing calculator. So you may go ahead and do that, and I will pull it up on the video here. Okay, so here we are graphing our function x to the 5th minus 5x cubed plus 2x plus 4. So we'll go ahead and take a look at that guy. This will take a second, but of course you're entering it in your calculator now to compare. So let's go ahead and take a look at that guy. Okay, now if you want your graph on your calculator to look like this one, I have an x min of -4, an x max of 4, an x min of -10, and an x max of 18, and it kind of centers the graph nicely, and you see what's going on here. So we think back to what we were just talking about, and we realize that at 0, that 4 was the dominant function. And at 0, our function is looking like 4. Just for an instant, just at that instant 0. If I go back home here, set this on equation 2, and graph a function plain old 4, this takes a little bit of time while I'm recording and gets a little bit blippy, but this will all work out. And we take a look at that graph. At that very instant where I put the red circle, you see these graphs are the same for that instant. But remember, the +4 was only in control at 0, and then who was the next one to kind of exert itself on the result was the +2x. Well, what does the graph y equals 2x plus 4 look like? It's a graph that goes through 4, positive 4, has a y-intercept positive 4, but has a slope of positive 2. So let's go back home and let's graph 2x plus 4 and see how it maps along this graph. And now you see the graph starts right where it's supposed to. Here's our 2x plus 4 as we head out. And certainly the graph doesn't look like, the blue graph doesn't look like 2x plus 4, but it sure does right through here. It looks like 2x plus 4. Right along this spot, right through here, we've got a graph, y equals 2x plus 4. Looks pretty good. Okay, so we continue. Graph -5x to the third, we realize that one took over for quite some time, and the graph was being most influenced by it. So let's go ahead and go back and graph these three terms. And we'll clear off some of this. And now look at the graph. Here we have 4 was in total control. Passed the baton, wanted to look like have a slope of 2 going through there. Now you're going to say, oh, it doesn't look like a slope of 2, but realize we're not in scale here. I have a graph where the x maximum is just min-max -4 to 4, but y is running from -10 to 18. So trust me on this one, we know that was a slope of 2. But eventually that 2 starts getting beaten down by this -5x to the third, or that 2x starts getting outpaced by the -5x to the third. It exerts itself and pulls it in its direction. And that's what the graph of -5x cubed plus 2x plus 4 looks like. And it maps our graph pretty well. But of course, who is ultimately in command? By time we got to 3, remember, by time we got to 3, or -3 in this instant, the dominant term was this x to the 5th. And that is why this graph really wants to just look like x to the 5th. And you're going to say, well, there's a lot of wiggling going on through here. Yes, there is. Let's go ahead and take a look at this, though. So I'm going to go back home. I'm going to graph plain old x to the 5th. and graph this guy. And you're gonna say, well, those don't look alike at all. Well, let me start to zoom out here. I'm gonna go x min. Let's just go. I'm just gonna go -8 to 8. -8 to 8. And then I'm going to do a zoom fit, which you have on your calculator. You have an option to zoom fit, which basically keeps the x-axis the same and tries to make as much of the graph as we can show. So it's going to have to chase up some pretty big values here. So I'm going to zoom fit this guy. And now you see my Y values are going up to 36,000. And take a look. That wiggling is pretty insignificant on that kind of a scale. And we only see a little difference at the end here where the red or the maroon graph comes off of the blue. And I'm only going -8 to 8. Let's go -20 to 20. Hopefully your calculators will handle this, not 220. 20. And I graph that guy. And then once again, I'm going to hit zoom fit. And now you might be able to see a tiny bit of blue creeping out. But if we view this graph from these two graphs from far enough away, it would be really easy to mistake to say they're the same graph. They both look like x to the fifth. Remember, it was only between 0 and 3 where these had really much influence over that x to the fifth term. So that is why that's a technique that I refer to as sprinters, intermediate runners, distance runners. It's a marvelous power tool for you to use down the road. And now we're going to play some games with your graphing calculator. If you are at home and didn't have an opportunity to see this, you can get with some friends. We're going to graph the McDonald's arches, and we're going to graph what I refer to as the grand piano graphs, and we're going to just graph a lot of different graphs where I'm going to, in fact, I'm going to have you graph them. I'm going to draw a picture of them, and you're going to have to come up with the function that will create that graph. It's a great exercise in showing that you understand sprinters, intermediate runners, and distance runners. Hope you enjoyed this. Hope you got something out of it. This is probably, unless you feel like you're 80, 90% comfortable with this discussion, this is probably worth viewing again. Thank you. Look forward to having a great year.